Okay, so what's the story today?
Okay, I'm going to try to do a lot of the same stuff, try to explain a lot of the same ideas that I was trying to explain last time. I'll try to do it slower, more calmly. Hopefully explain some things better.
Uh-huh.
So I'm going to start out, I think, with a sort of lowbrow section and then a sort of highbrow section. As usual, you know, who knows what lowbrow means and what highbrow means. But and of course, you know, little bits of lowbrow will get into the highbrow and vice versa. So sorry, I have a horrible problem with ink pens versus virtual ink pens. Okay. So we're interested in Z mod 3 torsors over some number field K.
Huh?
And
Sorry. Go ahead.
we're going to start out with a choice of K, which makes the problem easier and therefore allows the discussion to be somewhat more lowbrow to begin with. So, and that choice is K equals the Eisenstein field, which for some reason I'm notating like that, a little E for Eisenstein, and it's like the Eisenstein rationals as opposed to the Eisenstein integers.
Yep.
And you know, so we're interested in this ultimately we're interested in this very Tanakian viewpoint towards these torsors. But since this is sort of lowbrow section, maybe I won't overemphasize that yet. And well, so it turns out that well, maybe we will give at least since this is the easy case, we'll give a sort of Tanakian description of these torsors. So you can say that it's and this description of Z mod 3 torsors is valid only because we're already working over the Eisenstein field.
I guess a field over which Z mod 3 splits.
Exactly. That's what I should have said. Yes, that's right. And the Eisenstein field is the premier example of that. In some sense, the universal. Well, probably in some sense the universal example of that. Mm-hmm. So when that happens, when Z mod 3 splits over the field, then we just say that a Z mod torsor over K is equal to a line object L together with, I guess I'll use my abbreviation TW for together with, line object L together with a trivialization of let's trying to decide which way to write, a trivialization of the third tensor power of the line object. I'll call that F. The letter F probably stands for framing. I guess framing, trivialization, they're kind of frame, trivialization, they're kind of similar ideas here. Yeah, so that's what it is. And so by similar,
I don't know. For the pedantic listeners, you should stick a little isomorphism sign on that arrow, I guess, or whatever, or say that it's an isomorphism. Yeah, that's.
Yeah, I'm gonna put my little ghost.
Oh, okay.
Pointing in the other direction. I guess other people put like a little equation thing.
Yep.
Okay. And yes, thank you for that correction. And so then by our tricks, like the same kind of tricks that we used in the case of Z mod 2, since you're working over a field where, you know, there are no non-trivial line objects, there are no, I guess there's no non-trivial vector space objects. It's just the standard vector space is distinguished by their dimension. And so that enables this sort of gauge fixing, so to speak. And that results in this concrete lowbrow description of the classification of these torsors by saying that what it's let me think. I want to say something like it's elements or quantities in K, in this field K over which the group splits. It's like sorry, that's some sort of very eccentric spelling of quantities. Let me try to fix my spelling there. Quantities in K. Ever say non-zero quantities? You know, or invertible under multiplication. That's equivalent to the field. Non-zero quantities in K, but up to, let's say, up to a cube factor. And I guess we've joked about calling these things. Is it true you can actually get away with calling these things cube-free quantities or something like that?
Yeah.
Or cube-free Eisenstein integers or something like that. But it's you know, that's a little bit too much gauge fixing. It's perhaps better to think of it as these equivalence classes, you know, up to a factor of a cube. And so how does that classification work? Well, if you know, if the quantity is, let's say, A, then the corresponding I want to say that it corresponds to taking the cube root of A. But I realize I'm being sloppy there, but maybe we can get away with that for a moment, right? Because again, there's the idea that there are two different torsors that both have the same cubic extension by cube root of A. But
what do you mean by writing the cube root of A? What is
this generates the field extension that sort of is the torsor, except that it's right. It's slightly inaccurate to say that it is the torsor because there are two torsors corresponding to this cubic field extension of the Eisenstein field.
But the first description was more accurate. Yeah.
Well, I mean, we're saying that you know this extension is the same as this extension, A times a cube, where you know B is again a quantity in K. I mean, right? We can see that those are the same field extension.
So what you're doing is you're so what is the line object? in this? I mean, I know you said they're all isomorphic, so it's a question.
Yes. Okay. Yeah, that's a fair question. So, so let's see. It's, we have this picture. Okay, maybe you're telling me that I should have called it F or something instead of A. Is that what you're telling me, that I should put? Let's see, we have F here. Yeah, okay, I guess that's right. In the
So you're not telling me what yet. I mean, you're just writing the same thing that you wrote before so far, but okay.
Well, but I'm saying that if we have another one, I'm saying that, this idea of comparing them. So right, A is just another name for F, but it's in this coordinate system where we randomly, if we had a model for this, then you can just pick, you can use the standard coordinate system for, well, you just pick a coordinate system for L. You just pick a frame for L, and you use that to think of this arrow F as just a number. Yeah, just a quantity in K.
So you're identifying L with 1, and thus identifying L tensor cubed also with 1.
Yes.
And then F is just multiplication by A.
Yes.
Yeah. Okay.
That's right. And now if we have another one, F prime, coming from like maybe A prime, but expressed in this randomly chosen coordinate system, this gauge fixing thing, then you can think of them as equivalent when there's right, so what do you need? You need like you need a morphism from L to L prime, and it should, let's call it C perhaps, or something. No, well, no, I'll call it C, but it's probably really just B again. And this would be, so to speak, yeah. C, I was going to write it as C to the, like that, but that really just means C cubed. And this over here is, C to the 0th or something like that, which really means it's just 1. And so F and F prime are differing by a cube in this gauge fixed picture. And so that's how the classification works. And yes, so right. So what was I?
Yeah. Adjoined cube root of A. Those two things of that sort for different A's would be equal. Is that right? If the Z mod 3 torsors that they're describing are isomorphic. Is that right?
Or they would be isomorphic if they're isomorphic. I mean, isn't that good enough? Do I have to think about whether they're equal in some sense?
Oh, maybe not. I don't know. Yeah. Okay. I think of, okay. I guess I was just thinking of K adjoined cube root of A is actually a specific subfield of the algebraic completion of the rationals. But anyway, but if you could think of
it more, then if you think of it that way, then yeah, probably that's probably true. Yeah, but I was being a little bit.
Okay, if you think of it more abstractly, it's just like you throw in extra element. The cubes to A. Okay, I got it now. Yeah, so it's
okay. Okay, but so
what is this thing?
Yeah.
What is this? This is like some way to try to make seem quite trivial something or other. So I mean, it's a classification of.
I mean, it's something that's already so trivial that perhaps it doesn't need much help to be trivial. Just, you know, the classification of Z mod 3 torsors over the Eisenstein field is already pretty straightforward, but we're just putting it into this language that I like.
I thought what it was like a new way to think about the problem of classifying these kind of field extensions where you take, that is, it's not yet clear. If you think about it that way, it's not yet clear how it's helping, but it may be like clear that it like it's like that the old problem is like can be thought of in a sort of beautiful way in terms of line objects so far.
Yeah, I mean, right. I mean, remember this whole thing is supposed to be a nice functor from the representation category, you know, from the Tanakian viewpoint. So this is a little bit of the highbrow viewpoint. We're supposed to be able to think of this as a nice functor, meaning tensor preserving, basically tensor preserving left adjoint, from the representation category of Z mod 3, which is already splitting in this case, to the vector spaces over K. And so the point is that in that representation category, we have a nice object, which is going to get taken to it's really the group ring itself, right? The group ring itself is a representation, and that representation is going to get taken to a commutative ring in you know, because the functor preserves tensor product, it's going to take us to a commutative ring object in vector spaces over K, and you can see, you know, it's going to be a cubic extension of K. And so that's how we're right. So there's a very straightforward way to extract a cubic extension from one of these torsors. It's just, you know, thinking of the torsor as this functor, as its associated vector space functor. You're just applying it to the group ring. As the group ring as a representation, the associated vector bundle, so to speak, of that is this field extension.
Yep.
And okay, so that's some sort of preliminary. And it looks like I'm still learning how to use this whiteboard a little bit better. So it looks like I'm going to a new page now by pressing something.
Yep, that.
Okay. And okay, and then if necessary, I can go back to the previous page. Okay, but now I'm still trying to think in a lowbrow way. I want to think about, you know, so we started from the Eisenstein field, but I now want to think about, you know, what happens if you go back to the rational field and think of the Eisenstein field as an extension of that, and then this cubic extension as an extension of that. And so that's going to be a 6th degree extension. You know, we had this 3rd degree extension of, I think it's called the degree. I hope it's called the degree. That's what I'm calling it. The 3rd degree, we had the 3rd degree extension of the Eisenstein field, but the Eisenstein field was itself a 2nd degree extension of the rational field. So you multiply them together and you've got a 6th degree extension of the rational field. And, you know, it's a nice abelian situation, so it's still Galois. It's pretty obvious that it's still going to be a Galois extension. And so what am I trying to say? I'm trying to say that
when you say it's an abelian situation, you don't mean that the 6th degree extension is abelian, right?
That's right. I don't. I don't.
Just checking.
But somehow the situation is tame enough that that this 6th degree thing is going to be a Galois extension.
Uh-huh.
I don't want to go worry about that. What that
That's
means.
fine. I
I
don't
always have
wanna-
trouble remembering exactly what that means. But yes.
Yeah, that's fine. I'm happy to
Okay.
get over that.
Okay. But so it's going to be a Galois extension, so it's going to have a Galois group, a 6-element Galois group because of the 6th degree extension. So that means there is basically 2 choices for what that group could be. Is that right? There's only 2 6-element groups, basically, one of which is abelian and one of which is not abelian.
Mm-hmm.
And both of those can occur depending on which Eisenstein quantity we took the cube root of. And so the low-bound problem here is to tell which Eisenstein quantities, when you take the cube root, you know, which of those Z mod 3 torsors will combine with the Eisenstein, you know, will when you look at it starting from the rational field up, some of them will look like a Z mod 6 torsor, others of them will look like a 3-bang torsor. And
Can you tell me one that gives me a Z mod 6 torsor?
I think if you pick one at random.
Really? Those are the more generic one? Okay. Wow.
Yes.
Oh, okay. Huh. Less symmetry, I guess, or something like that. I don't know. Why am I saying less symmetry? I don't know what I mean by that.
It might be true. But I don't know. I'll have to think about
I don't
that.
know what I mean by that, but
Yeah.
Okay, that's weird. So like what if I took the cube root of one of the cube roots of 1? So I had the Eisenstein series, it has these cube roots of 1. The most obvious cubic extension of that is to throw in a cube root of one of those. Am I doing it wrong? Then we're getting like a 9th root of 1.
Yeah, no, that's correct. That is a that's going to give us a Z mod 3 torsor over the Eisenstein field. And I think we actually talked about this one. I think we actually talked about this one, but
yeah,
maybe I talked about it so fast that it went by too quickly or something like that.
It was probably in part of this 63 business. You had like 9 times 7.
Yes, yes, that's right. That's right. That is what the 9 was doing there. That had a lot to do with why the 9 was there. That's right. That's right.
Okay.
I think that is basically why the 9 was there. But
Okay.
now I'm getting the feeling that you're trying to make me look bad by deliberately picking an example which, you know, will give the non-generic thing. So this is actually going to give us an abelian one. This is going to give us a Z mod 6.
Oh,
You know, a moment ago,
yeah, that's right. Wait, what did you say is the generic one?
the generic one is the non-abelian one.
Oh, I thought you said the opposite. Wow. That's why I was acting so shocked. No, I would guess that.
Well, unfortunately, we do have recording this, so we can go back and find out if I said it wrong.
Okay. Well, anyway. So okay, no, now I'm not so. I was confused. So I want to see. Okay, I want to see a. Yeah. Okay. Good. So you're claiming that I picked a non-generic one.
Right, because you did pick a very special one.
Yeah. Well, I picked like the only one I could think of. So, well, that's not true. I picked. No, it's not the only one I could think of. Okay, so what's like this? The simplest. What's a really simple generic one?
I think it would work if you took cube root of. I'm guessing. This is a wild guess, but maybe you took cube root of 2, cube root of 3, cube root of 4, cube root of 5. I'm guessing that those would give us 3-bang. I should know, of course, the answers to those, but and like I say, if you just pick kind of a random Eisenstein quantity, that should probably most of the time, in some sense, most of the time. Well, so to
well, yeah. So I never studied Galois theory, so like I have no idea like what. So like if I take the Eisensteins and I throw in a cube root of 2, I'm supposed to be able to like find some number that has. What am I trying to say? I'm supposed to be able to like see the three bang actions. I'm acting on something somewhere there.
Yes. I mean, right. Let's just think about that for a moment with the cube root of 2, just to see if it works. Okay.
Yep.
So what are we trying to say? So there are 3 cube roots of 2, seems like, and you get them by multiplying each other by, if you have one of them, you just multiply them by cube roots of unity to get other cube roots of 2. And
I'm
hoping it might be almost obvious that it's going to be free bang, but go ahead. Yeah.
So are you hinting? It sounds like you're hinting that the the Galois group of this 6-degree extension, it acts to permute those 3 cube roots.
Yes.
So they're like all created equal, so to speak.
Yeah, and right,
okay.
and if you do it by applying, I mean, what am I trying to say? That right, you can multiply. I mean, these cube roots of 2, they're all, like I say, they're all, they're all right. They're yeah, yeah, I'm right. I am claiming it's so obvious that I don't know how to prove it. That you can get any permutation of these 3 cube roots, and to get the ones of what is that called? Is it called the signature of a permutation? Is like even or odd or something like that? What is that called?
Sign.
The sign of a permutation? Okay, that's similar to signature. The sign of a permutation is even or odd, or plus or minus or something like that. And to get the odd ones, to get the negative sign ones, that's where you extend the involution of the Eisenstein field. That switches the 2 cube roots of unity. Somehow that's going to end up giving you. I'm hoping if you stare at that, you can sort of see that that's going to work out like that. So yeah.
So is it like, so here's like a possible hallucination. So I've got these 3 cube roots of 2.
Yeah.
One of them is real. And so I might think that it was like different than the others because it's fixed by complex conjugation, and maybe, and I was thinking, like, well, complex conjugation is the symmetry of the Eisenstein integers, but maybe that's like a delusion. Maybe that's just like a maybe you can extend the symmetry of the Eisenstein integers to the usual complex conjugation on all complex numbers, but maybe that's not the only way to extend it so that.
That's right. There's nothing in the field itself that tells you which one is the real cube root of 2. The others are algebraically just as good. There are automorphisms. So, so the information as to which one is real is not recorded in the algebraic structure of the.
Wasn't there like a game show where you had like 3 people pretending to be something and you had to guess which one was the real one?
There are probably a bunch of
like an old famous.
Like certainly, yes. There's that. It sounds like you're talking about To Tell the Truth. Yes.
Yeah. Right. Okay. Yeah. So okay.
Carlisle and
yeah. So somehow like there's no way to tell which is the real.
That's right, and that is the way I think of it.
Yeah.
Have I actually thought in terms of To Tell the Truth? I'm not sure, but I do certainly think of it in that sort of.
Okay. Yeah. Okay. Good. Yeah. No.
In that sort of paranoid way. I think of it in that paranoid way where you're not sure whether people have switched places, when you looked away or something like that.
Okay. Good. So now have an intuition maybe for both of the two cases here.
Okay. And so now I think I'm basically going to tell you a kind of lowbrow rule for being able to tell the difference. I'm going to describe, some fairly concrete way how to tell which ones give the Z mod 6 torsors instead of the 3 bank torsors. So, which ones are the non-generic ones. And and then, I think it'll make some sense that this works, maybe, possibly based on things that we've said previously. But to really prove it, that will probably be in the highbrow section or something like that. But anyway, I'm going to make an attempt to correctly state lowbrow description of these sort of abelian ones, these ones that give the Z mod 6 instead of the 3 bank. So how do I say this? I've written down somewhere. Maybe I can say it without checking my notes. Let's see. So I want to say something like, that if you're taking, if you're taking cube root of, I can't remember whether we've been calling it A or F. Maybe we've been calling it A, or sort of depending on how you blur the notation.
Yeah.
If you take the cube root of A, and if A is the thing that you're using to get the Z mod 3 torsor in this way, then if you take A squared and then take its conjugate. So right, we have to be a little bit careful what conjugate means here. This is, sort of like a complex conjugate, but it's really the Eisenstein conjugate. And again, you have to be careful because of like what you were saying about how, you can't always tell what the real things are. You can't always, but in this case, it is sort of unambiguous enough that, the Eisenstein field has this unique involution. But if I wanted to make the notation better, maybe I would say C for conjugation, sub E for Eisenstein, and then I would say A squared or something like that. But anyway, the condition is I want this to be equal to the original A. I should say, I didn't say that right. To be equal to the up to factor of a cube. A cube factor. So that's the answer. Now I gave some concrete examples last time. Like I think I gave an example where I started out with the, if I remember correctly, I started out with the Eisenstein non-prime 7. And as a non-prime over the Eisenstein integers, or sometimes over the Eisenstein field, it factors. And we did eventually figure out how it factors. And was it something like 1? Again, you'll have to check and see if I got it right this time. 1 plus 3 times 1 to the 1/3 times 1 plus 3 times 1 to the 2/3. Does this look like that is indeed 7? I think that's correct. I think it's going to be 1 plus 9 for the sort of outer terms. And which is 10. And then it's going to work out to -3 for the inner terms because of the way, the cube roots of unity balance out.
Okay.
What?
Okay.
You don't like that?
Sorry, I don't know what's confusing me about it. I went through all of this type of thing last time.
I mean, is it true there probably are good things to be learned from staring at the picture, of where these numbers lie in the grid.
Well, that's what I'm doing.
Should I try to draw a picture, or should you draw a picture?
So the main thing to know.
Yeah. Again, I'm sort of hoping we'll both be really drawing together here. You're not inspired to draw pictures here?
Oh, okay. I forgot. I completely forgot. I will try to do it now. Let's see if it.
Okay. I mean, this is great for me because I'm too lazy to draw the pictures.
Yeah, well, anyway, this is a chance where I might actually do it. Okay, yes, okay. So what I imagine here is like you got it takes a while to get my
okay.
lined up here. Oh, there's also a time lag. Oh no. I'm gonna turn off my image because it's really hard to draw when you have a
okay, that sounds I'm very helpful at turning off the video image.
Yeah. Okay, let's try that. So
it's a little bit better.
So basically got this guy and this guy. That's 1 to the 1/3. And
yeah, it bugs me a little bit that you're imposing these rectilinear axes over this very hexis or triangular screen.
Yeah, it's true.
But that's okay. Yeah, okay, but go ahead.
That it's annoying, but that's supposed to be, well, it doesn't look pretty good, but that's halfway.
This is fine.
That's halfway from there to there.
Yes.
And so,
right. Halfway from
here, from -1 to 0.
Yeah,
so it's like
right.
-1/2.
Halfway in the horizontal direction, yes.
So anyway, so when we add them, we get we get that. Okay. And so 3 times it. Yeah, I guess it is working. So what I'm saying is that 3 times the sum of those two guys isn't -3.
Right. I mean, the slogan I just used to convince myself that it's going to work without having to draw trinity pictures is just that, all of the third roots of unity just balance out to give the origin. So any 2 of them will give the negative of the remaining one, or something like that.
Yep. Okay.
Oh, okay.
Okay. I don't know why I had to do that over again, but yep, I did.
Right. Well, so I did this basically just so that, how do I do that? So that I could have a nice handy actual Eisenstein quantity right there. That is not its own conjugate. In fact, it's the other factor that is its conjugate. It's Eisenstein conjugate. And so let me just call this, let me call it D for the moment, okay? So if I take, I'm hoping this is gonna work. It worked in practice. I don't know if it's gonna work now. D times, again, I'm going to use a bar for conjugation now. It's the Eisenstein conjugation. D times like that. And D was a totally arbitrary quantity to begin with, except that I'm specializing into this particular example just to make it concrete. But just by being of this form, I'm hoping it's going to have the property that I said, that this is going to happen. So let's try that. So what are we doing? We're taking first, we take its square. Is that right?
Yep.
So it's D squared times D bar to the 4th.
Yep.
And then I take the conjugate of that.
Yep.
So the conjugate of that is equal to maybe D or squared.
Yeah.
Times d to the fourth.
Right, and so that is your original quantity times
Apart
d.
from, yes.
Huh?
Yes, apart from a factor of d cubed, I believe. Is that right?
Yep. Mhm.
Right, I mean, what is this? This is a little common sense prescription for, fairly common sense prescription for how you can get things that satisfy this non-generic condition. And right, it's like they're lying on an axis or something, you know what I mean? A sort of skew symmetry axis or something of some kind. But it's a little bit of a funny kind of skew symmetry axis because I'm not sure I can visualize it yet, because it's involving sort of multiplicative structure, squaring, and also that it's got this, up to a cube factor thing going on. So I don't know, maybe it's like,
Yeah.
dense among the, I don't know, but it does seem to be the answer. I've tested this out, and this seems to give the ones that that actually give you these abelian things, these Z mod 6 torsors over the rational field, instead of these 3 bang torsors over the rational field. So
yeah, for the example that I first mentioned,
yeah,
where A was a cube root of unity, then those two guys are actually equal on the nose, not just up to its cube factor.
Yes, that's very unusual, but that's true. Yes.
So that's like
right.
super special. Yeah.
That's right. There's something very special about that example. I have a feeling there's some famous, because right, I mean, we're talking about these non-generic things. That's even more non-generic. It's like the special among the special, and I think it probably has some special significance, but I don't really. Well, I don't know. I was going to guess it had something to do with the buzzword art and Schreier that I hear about, but that's a stupid wild guess. Might have no connection whatsoever. So yeah, so this is a kind of lowbrow answer to this lowbrow question, but now we're going to try to understand this in a somewhat higher brow way using our Tanakian, so-called Tanakian philosophy.
Before you do, I'll just say there's
Yeah.
like one thing that
Yeah.
decision you made that surprised me a little bit, which was that you could have decided to study the question of cubic extensions of, for example, the rationals.
Yes.
Instead, what you did is you say, first we'll go up to the Eisensteins, and then we'll
Yes.
look at, wait a minute, what are we doing?
I mean, we're studying cubic extensions of the Eisenstein field, and then we're sort of composing them with the Eisenstein field as itself an extension of the rationals. And so we're getting a 6th degree extension,
right?
And we're analyzing whether that 6 element Galois group, whether that is Z mod 6 or 3A.
So like you could also try doing this, maybe it's just turns out to be like more annoying.
Yeah.
Take the rationals, take a cubic extension of it, and then throw in a cube root of unity, so or whatever, extend.
Yes. Yes.
And then you'd be in a situation.
Yes.
At the end.
Yes, and that's the non-generic.
A lot of times would be like, actually, it would always be of this sort, right? Yeah.
That's right. That will, right. And it has something to do with the way that, right, I mean, I think it has something to do with the way that, right, Z mod 6 has, Z mod 2 and Z mod 3 both as, they're both subgroups and they're also both quotient groups, whereas 3 bang only has Z mod 2 as a quotient group. Did I say that right? No, it only, the only one that has as a quotient group is Z mod 2. It does not have Z mod 3 as a quotient group. And that, that means that you can't get the 3 bang by first doing the cubic extension and then doing a quadratic extension.
Oh, I see.
Because, you sort of unfold more of the group each time you make an extension. So yeah, it makes sense that, this.
So you're covering more ground, covering more cases by doing the cubic extension after the Eisenstein extension.
Yeah, I mean, you could all, yes.
You cover all the
Yes,
cases.
yes, that's true. That's true.
You cover the other way with more.
That's true. And but also in the back of our minds, it's sort of good to keep in mind that we did in fact start with the problem of, what happens if you have the rational field and then you have a Z mod 3 torsor over that. But somehow that forced us to think about the starting from the Eisenstein field. Go ahead, say it again.
Yeah, no, that's why I brought this up, is because
Yeah,
it felt like the original question had gone away and you replaced it with this other question.
Right, but that question, from the highbrow viewpoint, we're supposed to see how that question is still the motivating question. But there is this interesting, associated lowbrow question of, when you take these cube roots over the Eisenstein field, which are the ones that give you the 3 bang and which are the ones that give you the Z mod 6? And again, as usual, I'm always hoping that I'm not making, really bad, horrible mistakes. But in particular, you got me slightly scared. I mean, right? The idea that it sounds like you've got me claiming that when you take these non-generic cube roots, that you actually manage to get them to be no way you can permute them all 6 ways. There's only 3 ways that you can permute them. And I guess that's true. And then maybe that's even obvious. I mean, in that one case of the 9th root of unity as the cube root of the 3rd root of unity, maybe that's obvious that you can't just permute those. Yeah, I think that's right. Yeah, if you there are 6 primitive 9th roots of unity, and if you think of how that Galois group works, it's not 3 bang. It is Z mod 6. It's basically the multiplicative GL1 comma Z mod 9, which is this 6-element multiplicative group of this 9-element ring. So I shouldn't be worried about it because I just gave what sounded like a pretty good argument, but somehow you still managed to make it seem scary to me. I just hope I'm not screwing up. So yeah, so we're okay. So now we sort of did something lowbrow, and now we're going to try to now our attempt is to find the secret highbrow royal road that's underlying all of this. So let me go to another blank page here. So now what are we trying to do? Well, so now I'll try to restate the result, which I did sort of state last time. I'll try to state it in a calmer and better way. But the result that I think you said you sort of liked last time, which was, again, so now we're trying to think about the representation category of Z mod 3, where it doesn't split, in other words, over the rational field, as opposed to the Eisenstein field where it does split. So we're looking at the representations of Z mod 3 over the rational field. And so basically there's 2 irreps, and they're not all one-dimensional. There's this, 2-dimensional irrep. It sort of feels like it's 2 one-dimensional irreps stuck together or something like that. But it's, yeah. And So that's a category. That's a theory in our doctrine. That's the syntactic category of a theory in our doctrine of whatever we call them, total two rigs or something like that. And we want to understand what it's the theory of. We want, a sketch of this theory. And I sketched a sketchy sketch of that last time. And now we're going to try to understand it better. So, but it's really going to exploit, right? And this is what we were alluding to some minutes ago, that this is really going to exploit the work that we did where you start from the Eisenstein field. So the description where you start from the Eisenstein field, let me draw it once again. So what did it look like? It looked like the tensor unit is mapping to something. So mapping the tensor unit by an invertible map is giving a frame for this object. And so the object that we're giving the frame for is this third tensor power of this line object L. L presumably is supposed to stand for line object. I guess in this case, we probably don't even have to worry about having some independent assumption that L is a line object, because the fact that it's got a third tensor power that is trivialized, that is isomorphic, that seems like that's probably going to, yeah, that, right?
Mm-hmm. Yep. Yep, its tensor square is its inverse, and so
yeah.
Yep. And that sort of has something to do with the trick you've been playing.
Yeah, I guess there is one little glitch that I might be being a little bit sloppy about here. We did, how do we know that this? It's only because this is a line object. I guess it's only because this is a line object that we know that the symmetry for the braiding is a bosonic braiding rather than a fermionic braiding or something like that. But I don't want to worry about that too much.
Oh, okay. Yep.
So, and I guess I call this F or something like that. And that's like that little picture is sort of a sketch of the theory. I mean, I'm probably stealing somebody's terminology of sketch, right? That they use in other doctrines or something like that. But I think it's okay to do that. To me, sketch sort of means categorified presentation.
Yeah, not too terribly long ago, Highland and somebody came out with a paper about nodal sketches.
This is something like that. This is something like that. Or this is my ad hoc version of something like that.
Yeah, I was sort of amazed that it was like so recent that somebody.
How recent? I thought it was, I thought it wasn't that recent. I mean, maybe less than 10 years.
Yeah, well, that's right. Yeah,
that's yeah.
I mean, it's something
I don't know.
People could have tried to do a long time ago, but
sure.
Yeah. So anyway, it's because it's a very natural idea. So okay,
sure. But I'm just faking it in an ad hoc way because it's not difficult. In this context, it's not difficult. So, well, right. So we're going to sort of borrow from this sketch to create our new sketch. So it's going to be, right, it's going to be sort of, to start with, it's like a formal imitation of this. So we have E, which this is some, E kind of means you could say it's the Eisenstein field or the Eisenstein ring or something like that, but it's expressed in the doctrine. So it really means something like, take the direct sum of two copies of the tensor unit or something like that. And then put this multiplication on, put the multiplication on it, that makes it into the Eisenstein thing. Eisenstein ring, or Eisenstein field. Again, it depends. Yeah. And so we sort of want that theory sort of relativized to over the Eisenstein field. So we're going to have an Eisenstein linear trivialization this time. Well, so L is also going to be an Eisenstein line object rather than a line object. And this is going to be, the Eisenstein tensor power using the Eisenstein tensor product and the third one. And so I'll still call it F maybe. And I'm hoping that I saw, again, I'm being sloppy with the notation, inventing the notation as we go along, but I'm hoping that this is good enough. I'm hoping that I didn't forget anything there. It sort of seems like that the way I wrote it is sort of stating that this is basically a copy of a model of the original theory, but it's relativized to over the Eisenstein situation, E. Because I remembered to replace the tensor unit by E. I remembered to ensure that F is E linear, and I remembered, well, I didn't really notate it, but I said that L is an Eisenstein line object, and you can sort of tell that it has to be because it wouldn't work with an ordinary line object. And I notated the tensor power as being the Eisenstein tensor power. So hopefully this is good enough. But this is obviously not enough. Is it obviously not enough? What am I trying to say? I mean, somehow, right? We want, if I'm understanding correctly, what we want is we know we're going to need more than this. This is not a sketch of the theory that we're trying to sketch. This is not a sketch yet of the representation category of 3 bang before it splits. So we need to put in more stuff into the sketch to narrow it down, to constrain it further. But from the lowbrow point of view also, right, it's sort of like, the problem is that F is too free at this point. Right, we know there's supposed to be some sort of constraint on F. That lowbrow constraint we had. Well, how did the lowbrow, it said that F was equal to the square of its own conjugate or the conjugate of its own square or something like that. Up to a cube factor or something like that. And that's a constraint, and that constraint should be emerging in a natural.
Sorry, that was supposed to give the abelian case, the Z mod 6 type case?
Yes.
So like if you just stick with what you've got so far, what you wrote down on the page here.
Yes.
Giving you both those cases? Sorry, is this like?
I think that's right. I think it's something like that. Something like that.
Beautiful, this thing.
Yeah, say it again.
This sketch down below here is very beautiful. And so I was just wanting you to slow down and say what this is the sketch of, and let me just try to say it. So I mean, it's sort of so what is a model of this sketch in rational vector spaces? So it would be E would be a field isomorphic to the Eisenstein field. So you might as well just say it's the Eisenstein field.
Yeah, it has that involution ambiguity as to which is, you can't quite say the because it's.
Oh, okay. Yeah.
It's not factorially determined, but it's close. Yeah.
Yeah. Okay. So my image seems to be frozen with me staring up into the sky. Okay. I'm not looking at it.
Okay.
So okay. So I could call we've got an Eisenstein field E, maybe not the Eisenstein field.
Yes.
And in there, we have this. Sorry. In the category of vector spaces of that, we have a line object whose cube is equipped with an isomorphism to the Eisenstein, this Eisenstein field, the tensor unit. So that really feels like what we're doing is we're talking about first extending the rationals to an Eisenstein field, and then doing a abelian cubic extension of that.
Yeah, or something like that. I could try to tell you what I think it is.
Okay, sure, yeah.
So I think this is sort of like a categorified analog of like the kind of exponentiation that you do, for example, in synthetic differential geometry, where you take, you think of the tangent bundle of a space as being an exponential of the tangent bundle of space X as being an exponential of X to the power of the walking tangent vector.
Mm-hmm.
So this is something like, I think it's this original theory, the theory of a Z mod 3 torsor, but I think that's to the power of, I want to say something like to the power of is it to the power of the Eisenstein, the spectrum of the Eisenstein integers? It's to the power of something. It might just be to the power of the spectrum of the Eisenstein integers, or if that's not quite right, then maybe that's not quite categorified enough. Maybe I needed to categorify the exponent as well, in addition to categorifying the whole exponentiation process and everything, or something like that. But I think, I think we're sort of, I think we're sort of relativizing to the Eisenstein field in some way that's analogous to, the way synthetic differential geometry involves relativizing to the walking tangent vector when you're thinking of a tangent bundle as an exponential or something like that. Is that too annoying for you to think about right now? Too much of a digression? If it is, then we can just put it to the side and come back to it later.
I'll just ask one question. Yeah. I know that Levere has some...
and again, I'm not sure of this. I could be screwing up here again.
Yeah.
There's more of a chance of me screwing up about this than for screwing up on the rest of this.
Yeah, I was looking for an answer that sounded more like just,
yeah,
some kind of number theory situation that this was classifying.
Yeah. But I was just going to say that, right, there's some sort of, it's like, right, there's some sort of extension of scalars here or something that's going on. I'm not, that might not even quite be the right word. Some combination. Yeah.
I'll ask a question that may have a quick answer. So like Levere has some theory of things like tiny objects like this walking tangent vector, and I can't remember, exponentiating with respect to them.
Yes.
Property. Is that true? Is that what you're alluding to? Even?
I think we're probably exploiting that here. I think
what is that property? I don't.
It's basically that the exponential exists in certain cases. There are a lot of contexts where you just can't exponentiate by an exponent object unless the object is suitably tiny or small or something, some kind of smallness property. But even trying to figure out what smallness means in this context can be a little bit tricky. But there are some objects that function more successfully as exponent objects than other objects, than more general objects. And I think we're dealing with one here that, even though I'm confused about which one we're dealing with, I think it probably is taking advantage of tininess or something like that in a similar way to what Levere talks about.
Okay, well, let's continue.
Okay. Okay. So what do I want to say here? So again, this is supposed to be one of our goals eventually is to express what we're doing in a language that it really is part of the language of Galois descent, or that is very unified with the language of Galois descent, which you were trying to explain to us last time.
Mm-hmm.
And so just, keep that vaguely in mind as I try to describe this, as I try to embellish this sketch. It should be sort of embellished in a sort of Galois descent way, even if I don't know exactly what I mean by that yet. But all right, I've really got to get used to the idea that I can't just scroll on this whiteboard. I'm sort of stuck with the real estate that I have at the moment. But does that mean I should really redraw this one already? Because I need sort of more room down here.
Yeah, you're writing as if this was like an infinite sheet of paper. You like
yes, I've developed bad habits from
like to. You're writing like the way a politics professor uses the blackboard.
Why do they do that?
Well, they just, when they come in after some class in the humanities has occurred, if you're a mathematician, you come in and you see the blackboard, and like right in the middle of the blackboard, there's something like a word like legal rights.
Yes.
Like the only thing they wrote in the whole class. So.
Oh, okay.
But
your theory is that they wrote it and then they couldn't figure out where to write anything else or something like that?
Well, they didn't need to write too much. They just like,
oh,
yeah. So
okay.
You're acting like you don't have
right. Okay. So I think I'm going to try to work with this that I have, just try to squeeze it in. We'll see how it goes. So I want to say something like, how do I say this? We're going to take this thing and we're going to try to take the whole Eisenstein conjugate of the tensor squared of that. So this should be reminding of like, this is sort of like this sounds like a categorified version of the lowbrow thing. I'm sure it is a categorified version of the lowbrow thing in some sense, something like that. So how do we say this? I'm right down here. I want to have this thing that's like what it should be like. Okay, the thing in the red oblong on top, that is, F is sort of the name of that thing.
Mm-hmm.
Right. And now on the bottom, we want to sort of have the tensor square of F. But then Eisenstein conjugated or something like that. And then we're supposed to have an isomorphism from that. Well, actually, we're supposed to have, let's see, how does this work? So, right, I think it's supposed to be, I'm saying we're supposed to take the tensor square of F and then the conjugate of that. But, I'm not sure I understand exactly the way, right, what we really mean, perhaps when we analyze what that means, is it means, F is sort of built out of L, F relies on this object L, and then F is itself a morphism, and all that stuff is getting tensored and conjugated in the appropriate way. So I guess what I'm trying to say is that we're going to have L.
By the way, one thing you could have said before, I think, that is you could have said like the tensor square is isomorphic to the conjugate, instead of saying that the conjugate of the tensor square is isomorphic to the original thing.
Say it again. What's the choices?
So can you go back one? I'm not going to reinitialize my powers.
Yeah, I'm not sure I didn't already say what you said, but I don't know.
Okay. So that blue box on top.
Yes.
if you'd felt like it, you could have said A squared equals CE of A, I think.
Oh, yes, yes.
So
And
it's
there's
just like,
other ways we could have said it too, because they commute with each other, you know.
yeah, so it just sort of spreads out the work,
Yes.
emphasizes the analogy that like doing A squared, it's sort of like doing.
Yes, absolutely, absolutely. It very well may be more elegant to do it that way when you were.
So anyway, I was just thinking that it might or might not be nice to take on in your new slide here, your next slide, you got this blob, red blob on top, and you could imagine like hitting it with some kind of conjugation thing.
Yes,
Separately hitting it with some kind of tensor square thing.
that's right. That's right.
Or you could do what sounds like you're going to do, which is like hit it with both of them.
Yeah, yeah, and right. What you're describing is probably much more elegant and generalizes better for the general case or something like that. But I'm not being that elegant yet.
Okay.
Not even trying to be that elegant yet. But yeah, that's very likely true. So so let's see. Am I getting anything that makes sense? I feel like I'm in danger of making some stupid mistakes here. What am I trying to say? So we have L, it's an Eisenstein line object. What am I trying to say? So it's like we're supposed to have sorry. I'm trying to check my notes here because I might have something in my paper notes that would help me here, but it's also possible I made a mistake in my paper notes. Let me just check and see if I can see if my notes make any sense here. Okay, I think what's going on is that I started drawing something over to the side here, but I think that's not a good idea. I think that was from an earlier version of my notes that wasn't really successful. Let me try to see if I can erase this. How do you erase?
Oh, yep.
Okay. And okay, so we're going to try to do it something like the way you said or the way I said or something like that. Why is there? Okay. How do I get? Okay, let's see. Draw. Will that do it?
Yep, you get different.
Oh, and then I have to click a thing.
Thickness.
Okay. Okay, and I've got a color, which is perhaps blue at the moment. Okay. So, so how does this work? So, I think this should just be, sort of E bar, which is, right, that's a little tricky to interpret, right? I mean, it's the Eisenstein conjugate of the Eisenstein field. I mean, it is just the Eisenstein field. I have a feeling what it will work out to mean is that this arrow will really be the Eisenstein involution itself. These will both be the Eisenstein thing, and this will be the Eisenstein involution. But I'm not really sure about that yet. I'm trying to get this to work. Right. The reason I think that this, am I saying this right? The reason I think this should be the Eisenstein field is because, right, we're supposed to take everything on the top and take its tensor square and the Eisenstein conjugate of that or something like that. But
So you're gonna tensor square this thing next? Is that the idea or not?
yes, but again, it's the tensor square. Did I say this correctly? It's the tensor square over the Eisenstein. Eisenstein tensoring, I think.
Can you write the whole thing and then we'll talk about it? I'm just dying in suspense as to like what's.
I'm not sure I really got that far. I mean, this is kind of where I ran out of steam in my preparation. So I'm trying to figure it out as we're going along.
Okay.
And now I'm hoping, you'll figure it out for me.
Okay, what I thought you were gonna do is you're gonna write like E bar tensor squared, and maybe with a little, now you're suggesting we were like a little E under the tensor sign.
Yes, but then, I'm so lazy, I'm just going to exploit the fact that that's obviously still just E. I mean, or E bar or whatever, right? I mean, if you're taking the tensor powers of E over E, it's still just E.
Okay, okay. That seems like the opposite of laziness to me, but okay, fine.
No, I don't think it is.
I thought you could just take the top picture,
Yeah.
bar over everything, and put a tensor square over everything. It would be very
Yes. Yeah,
lazy,
that's basically it.
very, very lazy in the sense that you just like, you don't need to think.
Well, but you have to write more or something like that.
Okay, well, okay. Yes.
Well, okay, let's do what you're talking about over on the right-hand side at least. So what's that going to look like? That's going to look like L tensor squared.
Cubed.
No, I think this is squared.
Oh, I see. Just which, well, it doesn't matter which order are you then gonna
I don't know. Does it matter? I mean, let's see. It probably doesn't matter. Let's see. But right, the way you said it, it does sound like we would have the cubed on the inside. So let's see. So maybe your philosophy is better here. Let's see. Let's see. And right, I mean, it's probably okay to do it either way. It's just that if you like accidentally do it one way over on the right hand side and another way over on the left hand side, then we can get ourselves in sort of big trouble or something like that.
Yep.
But
Your laziness is like making you do a lot of work. I know some of you like think very hard about how to not work.
right. Well, okay. So I think this thing over here is, again, I'm being sloppy here, but I think there's just going to be, it itself is going to be the Eisenstein conjugation, just the anti-linear thing, the involution, which is, rational linear, but Eisenstein anti-linear.
Uh-huh.
And this thing over here is going to be what? It's going to be, let's see. See, okay, maybe you're right. Maybe this should have been. Sorry, this must be an eraser. Okay. How does this work? Draw. Okay, that's the third thing. And then we have tensor squared for the Eisensteins. And am I saying this right? Let's see. Is this going to work? How's this going to work? Let's see. So maybe this was right. Maybe this is supposed to be, let me think. L. I was thinking it was going to be, yeah, I'm having trouble getting this to work. L. See, maybe this is why I wanted to have the 3 on the outside instead of on the inside or something like that. That makes sense. Let's see. If I had like this thing G, I thought I was going to have this thing G.
Was there supposed to be
This
a
would
bar
be,
in there somewhere? And is that G supposed to be an isomorphism between something and something? Yeah.
yeah.
Okay. Uh-huh.
So right. So I think I want to go back and do it the way I had it. So is this making sense? Maybe this will be G cubed. Well, maybe it'll be G cubed conjugate or something like that. And this will be I want to say something like F tensor squared conjugate. Again, I'm not sure how well that parses, right? I mean, right, I have somewhat sloppy notation, but I'm trying to get this to all work out.
Uh-huh.
I think this is an attempt to sort of draw the sketch of the theory. And you know, maybe there are all sorts of ways, right? There are all sorts of ways errors could have crept in or jumped in or whatever.
Yep.
But I'm hoping that this is close to being correct. And you know, the main thing about checking whether it's correct is really just trying to check how well the notation works. How well do we really understand how this notation works? I mean, again, there could also be, it's possible that there might be some coherence issues. There might be coherence laws that are supposed to, for some good conceptual reason, go into the sketch.
Yeah,
I actually don't think there are any, but I could be wrong. Go ahead, yeah?
yeah, so it really does remind me a lot of Galois descent, because you've got
That's
this
good.
object in red, and it's a weak, it sounds like you're hinting that it's like a weak fixed point of something, because you're applying something to it.
That's right.
Flipping it with an isomorphism to that. And it's possible that you don't need the coherence law because you're not drawing the whole diagram, or you're acting by everything in the Galois group. You're just acting maybe by some generator or something.
Yes, yes. I'm hoping that it's because we're dealing with a simple situation where there's just one generator in Z mod 3. And I'm hoping that that's good enough.
So that looks promising to me, but what's then confusing to me is that,
I mean, it sounds like, I mean, let's get more specific. It looks like it's a weak fixed point of, if I understand correctly, of this tensor squaring followed by conjugation or something like that.
something like that. But then, okay, so then, yeah,
Maybe,
that's
but go ahead, yeah?
Yep. So what's confusing to me about that
Yeah,
is that if it were really Galois descent,
yes,
then the thing that it's a weak fixed point of
yes.
coming from some element of some Galois group, so that this tensor squaring followed by conjugation would be connected to some particular, it might be like a generator of some particular Galois group.
Well, I mean, yeah, I mean, there is something, right? So,
Well, so what is that? So I'm confused partially because there are like a couple Galois groups running around at this stage.
yes, but it seems somehow like it looks like it's all this Z mod 2 Galois group that's intruding into this.
Okay.
So what am I trying to say? I think it's this Z mod 2 Galois group, which is the, you know, the Galois group of the third the primitive third, the primitive third cyclotomic.
Okay, yeah,
The third cyclotomic or something like that. It's
okay.
that, I think it's manifesting in two different ways. One way it's manifesting as this, you know, involution of the formal Eisenstein field. And that's, you know, that's a Z mod 2 Galois group. But it's, and the other way it's manifesting is almost the same way, but somehow, I don't know. The other way that's manifesting is, what am I trying to say? That I mean, it has to do with this picture that we've got where we've got the cube roots of unity, including the primitive ones and the non-primitive one. And what am I trying to say? That, you know, I like naming these as 1 to the 0/3, 1 to the 1/3, and 1 to the 2/3. And the way it works is it really just has to do with, you know, this little 2-element Galois group that's interchanging the 2 primitive cube roots of unity. You could think of it as just being particularly from this point of view, with this notation for the roots of cube roots of unity, it's really just what am I trying to say? It's the multiplicative group of Z mod 3.
Mm-hmm.
That, you know, you take your favorite primitive cube root of unity, which has, you know, the exponent being 1/3, and then the other elements of the Galois group correspond to, you know, sending that generator to something else, and that just corresponds to, you know, like this is multiplying the numerator by whatever the corresponding, yeah. And in this case, the only non-trivial element of the multiplicative group of Z mod 3 is 2.
Mm-hmm.
And so basically that's, you know, where you send 1 to the 1/3 to 1 to the 2/3, and 1 to the 2/3 goes to 1 to the 4/3, which is really 1 to the 1/3. And so I'm hoping that somehow is responsive to what you were trying to figure out about how this maybe is Galois descent after we eventually understand how it's really working and everything like that.
Yep. Yeah. So it is. There's various confusing aspects, but it's good what you're saying, because the sort of obvious Galois descent we might be trying to do is Galois descent from the Eisensteins down to the rationals. And that's
exactly right. That's exactly right. And except, oh, descent. Okay, descent. Okay.
that is, we have
I still can't tell which way is the descent way and which way is the
descent is the hard way in this story.
Descent is the hard way. I'm not going to worry about that yet, but I agree that it is descent between those 2 endpoints. Even though I can't agree which one is up.
Well, the hard thing is to, like, it's supposed to be like easy to turn a cubic extension of the rationals into a cubic extension of the Eisensteins.
Agreed. And the descent is the hard thing. Okay.
Descent is supposed, don't blame me, but it's because they're thinking about things geometrically. So descent is the hard way, and so the hard way is to analyze when a cubic extension of the Eisensteins came from a cubic extension of the rationals. And the Galois descent philosophy would be, you write down what this cubic extension of the Eisensteins is.
Yeah.
And then you say it should be one of those things that's also a weak fixed point of the Galois group of the Eisensteins over the rationals. And so it looks sort of like maybe that's what you're doing here, although there are a number of funny features about it. And the thing that's like the most confusing to me is the sort of combination of the bars and this tensor squares.
Yes. I mean, that we need to clarify that, but it's almost making sense at this point. Yeah, it's probably just the same Galois group manifesting in 2 different ways, and it's just some sort of equivariance or something like that. Yeah, we need to clarify that. But anyway, what you just said, I was halfway following, and I will try to go back and listen to the recording to see that I really understand it. And it sounded like you said it a little bit differently from what I might have said, but it's probably the same thing. So I might have said something like that. You know, we've got this group Z mod 3 that we're interested in, and it sort of badly behaved over the rationals because it doesn't split over the rationals.
Mhm.
But what's a good covering to geometrically pull back to where it will split? Well, it's a really good one, that seemingly very adequate one, is to pull back to the geometrically pull back or algebraically push forward, geometrically pull back to the Eisenstein field, because that's
Yep.
practically designed to make this group Z mod
Uh-huh.
3 split
Yep.
over there. I wish I could get that. Sorry. Okay.
Well, that's what I'd call like the ascent part. And then and that's sort of typical of the descent philosophy, is that you take this
Yes.
annoying
Yes.
non-split situation and you go up to a big enough field so that it like becomes easy, which is typically the things split. And they even use the word split over and over again. So they say like a group representation splits, or
Yeah.
that,
Yeah.
like a division algebra splits. So when they, for them first there when they say splits, what they mean is like it becomes a matrix algebra or a central simple
Yes.
algebra
Yes.
split.
Yes. Yes.
Not really
Yes.
splitting in any literal sense. It's just like becoming.
Yes. Becomes very much more manageable, and you can. Yeah.
And so first you show that like, yeah, you can always make things tractable to a certain extent by going up to a suitable field extension. And then the work is the descent part, where you say like, okay, suppose we've got one of these nice tractable situations over the field extension.
Yes.
Could it have come from the original situation over the original field, and in how many ways? And so you take the situations over the field extension, and you notice that the Galois group acts on the groupoid of those situations, and you look for weak fixed points.
Yes. Yes.
So it's a nice philosophy.
Yes. I mean, yeah. I mean, yeah. I probably shouldn't make too much of an effort to express it in all different ways. But one of the intuitions I have is that this pulling back to a covering, that's like sort of an explosion process, separating things into pieces, more manageable pieces or something like that.
Uh-huh.
And then the descent is putting the pieces back together after the thing has been exploded, re-gluing things or something.
Yeah, that's
something.
Yeah. When you think about it more geometrically, these co-cycles that I was talking about, are the gluing data.
Okay.
Yeah, so maybe someday we'll really understand that well.
Okay. So let's see, how much time do we have left? Okay, we have about 15 minutes left. Right, this is the place where I should be cleaning up all these details, but I'm
Well, if you don't know how, then you shouldn't do it.
yeah, I
Well,
mean,
you could struggle, or if you have some other little thing you do know, it's like a 15-minute sized thing.
no, I think we're getting very close to splitting time. Splitting time? Quitting.
Quit and then let's split.
I think we're getting very close to quitting time here, because I'm, reaching a level of detail that I don't know how to finish off that level of detail.
Uh-huh.
But before we quit, let me try to demarcate what some of the things that we have done and some of the things that we haven't done yet. So what am I trying to say here? Well, okay, so try to keep in mind, with the way I sort of tried to structure the my talk today, even if I didn't succeed in really finishing up with a beautiful finish. But the way I tried to organize it was, I had this lowbrow preamble and I had this highbrow post-preamble. What?
Amble.
Amble. highbrow amble. And right, and the highbrow amble may have somewhat petered out, but you know, you're supposed to see how, if things had gone to according to plan, or if they eventually do go according to plan, then you're supposed to see how the lowbrow preamble is really vindicated by the highbrow stuff. That, and again, you're sort of supposed to see, I think, that, you know, it sort of feels like that lowbrow thing is sort of like a decategorification of this highbrow Tanakian viewpoint, right? Because again, let's just remind ourselves of what the alleged lowbrow claim was. So what was the idea? The idea was
Go back in your, why don't you go back in your
okay, just
slides there to help
just to get practice with using
my memory, yeah.
Is this a little bit too far?
Or
Or is it more like
that thing in the blue box on top was like
okay? And some of the other blue boxes too, like this one down here at the bottom or something like that. Yeah. So yeah, I mean, you see what I'm saying? That doesn't this look like a sort of almost in some sense, vague sense, like a decategorification of the highbrow thing? That, you know, we're getting something that's sort of like fixed under the combination of these two things, one of which, right, in this lowbrow thing, it's squaring and Eisenstein conjugation. And again, those are secretly the same element of the Galois group. Whereas in the highbrow context, it sort of seems like a little bit categorified, right? That the squaring was actually tensor squaring. And the Eisenstein conjugation was still Eisenstein conjugation, but it was somehow applying to these objects rather than just to these quantities or something like that. So we're trying to finish clarifying how this all worked. We you know, we're sort of pretending that we came very close to finishing this. And let's, you know, let's anticipate, being optimistic that we're really close to finishing this the right way without too many horrific mistakes. Let's try to anticipate some of the places where we should be going from here. So one of the places we should be going from here is that when we get this working for Z mod 3, we should be able to convince ourselves it's going to work for Z mod anything. I mean, so for example, we haven't done a prime power yet, unless we, you know, unless you count when we talked a little bit about Z mod 4 last time. But part of the point is that Z mod 4 is another nice, easy case. It is a prime power, and right, it's supposed to give you a sense of how all prime powers work. You know, Z mod 3 and Z mod 4 are very classical cases because Z mod 3 relates to cubic reciprocity, which is probably something to do with how Eisenstein's name got attached to it, the whole situation. And Z mod 4 has a lot to do with quartic reciprocity, which historically has some connection to Gaussian field, Gaussian reciprocity, quartic reciprocity, or also, I guess, Gauss, maybe other people called it biquadratic reciprocity. And yeah, the Gaussian integers, the Gaussian field, yeah, and there's probably something going on here historically about how Gauss and Eisenstein were some kind of associates or something. Maybe Eisenstein might have been
I think it's Gauss's student
or friend.
Yeah, I read somewhere that like
Gauss
sort of assigned Eisenstein the cubic case or something like that.
And he apparently, you know, gave him a good grade or something, except that maybe Eisenstein died too soon or something.
Oh, I didn't know that. Thanks. That's too bad.
Well, I don't trust me on any of this.
Yeah, well, I mean, I don't know anything else Eisenstein did, so that does suggest that, like, if someone's so good, and then just like you only know this one thing of theirs. Yeah.
I mean, but I thought Gauss spoke approvingly of the work that Eisenstein did. So I don't know, but again, this is just I'm just thinking again out loud about how, you know, if we can do the 3 case and the 4 case, then we can sort of convince ourselves we can do any of these cases. And then we can sort of put that all together into a version of art and reciprocity. In fact,
wait,
yeah.
one thing I wanted to ask, like you
Yeah.
haven't actually shown, in this whole story, you haven't really been showing anything, well, maybe you have, and I just can't absorb it,
Yeah.
anything about the reciprocity.
That's right. That's right. And in fact, I forgot about that, but I just reminded myself before you just reminded me. I just reminded myself to say something about that because I do have like 5 minutes that I could say something about that.
Great, yeah, no, because I'm dying to know how this.
Sure. I'm going to give, right. That's how I'll try to finish up here, roughly speaking. So what I want to say is, and this will be somewhat sloppy, but we'll really try to get this to work. So, so what I want to say is something like this, that when you have a Z, for example, a Z mod 3 torsor over the rationals, then you can induce it, perhaps slightly reluctantly, to push forward to a Z mod 3 torsor over a finite field. And I say slightly reluctantly because, right, it's not actually quite a ring homomorphism there, but it's sort of very, right, it's a slightly reluctant push forward. I mean, right, it's sort of like, it's like you pull back slightly, like instead from the Eisenstein field, you can pull back just to the Eisenstein integers. And that's a rather mild thing.
Mm-hmm.
And then you can push forward to the finite fields.
Yeah.
And, you know, so I'm cheating and being sloppy there, but right, it's like I say, it's a slightly reluctant push forward. And,
Yep.
You know, some of them go more quietly than others do. And the ones that put up a fuss, kind of, those are the ramified ones, I think. So, and this is also probably, now I can't remember that you know, you explained to me, you told me about some name that ended in Ashkey, but I can't remember whether it was Blashkey or Mashkey or something like that. Mashkey?
Yeah, Mashka.
Mashka. Okay, Mashka. Mashka. And that sort of seems like it's relevant here or something like that. I'm imagining that. So, right, I guess what I'm saying is that maybe that Mashka's theorem might tell us how the work that we're doing over the rationals, how we can like take that even further back to over some finite field, or to maybe it's like to over the to the integers or something like that, or and then forward again to a finite field or something like that. Like maybe that will.
Yeah, it's a sufficient condition for representations of a group to break up into 1D pieces over a finite field.
Yeah, so I'm optimistic that it's going to tell us when we can get away with applying the sketch that we've been drawing here to stuff over finite fields. So one
thing it shows is that they're like only finitely many finite fields. Like if you pick your group, there's only finitely many bad finite fields.
That's good. Yeah, that's right. So my vague idea that I'm trying to finish on here is that using this slightly reluctant push forward process, we're going to start out with a Z mod 3 torsor over, let's say, the rationals. We're going to push it forward or push it almost forward to over all of these finite fields. And we're getting a whole family, indexed family of Z mod 3 torsors all over these finite fields. And it's going to be over each different finite fields, you know, determined by its prime number, associated prime number. Each of those is going to give a different, you know, there's a choice of which
Z mod 3 torsors you could end up getting over each of those finite fields, and there's going to end up being a very simple pattern to which one you get, and the pattern is just going to depend on congruence in these abelian cases, like Z mod 3. And so what I think is going to happen is that, the basic content of the Artin reciprocity theorem, for example, is going to be, we're going to be able to put it in perhaps a slightly different form that says that any one of these torsors, like a Z mod 3 torsor, over the rational field or over any other number field, that it is determined by its push forwards to these finite fields, which are Z mod 3 torsors over these finite fields, and that it will follow a very simple pattern, and that's kind of how it's going to work. That's my big idea of how it's going to work, and that it's not going to be hard to prove, but that, there is stuff to prove there, but that it's going to work in a very nice way, and we may have to use something like Maschke's lemma theorem or something like that to clean up some of how this is going to work. Again, we may want to actually try going prior to the rationals. We may want to actually work out how this syntactic category of this theory looks like, even when you're originally just over the integers, or even before you get to the integers, maybe, just the natural numbers or something like that. We can, push it or pull it further back or something like that, and try to understand it at a deeper level or something like that. But that's the vague philosophy for this abelian case, which is perhaps summed up in Artin reciprocity. But then one more anticipation is, we're not going to just be satisfied with the abelian case. We really want to think about non-abelian cases, torsors of non-abelian groups, non-abelian finite or profinite groups over number fields, and that should be fun. That should be a fun thing to think about and try to understand. And then perhaps one more anticipation is it should also be fun to connect what we're trying to do to things like Kroneker's Jugendtraum and stuff like that.
Yeah, that's another.
And right. So there's really interesting ways to try to express Kroneker's Jugendtraum in sort of the language and philosophy of torsors, which again, these torsors that we're talking about, it's good for us to emphasize from the Tanakian point of view. And another way you can think of these is that they're just principal fiber bundles. And for some people, it really is good to use that language, right? That language of principal fiber bundles, because it encourages them to really think in terms of these geometric analogies to homotopy theory and things like that. I mean, perhaps you're supposed to know what a torsor is in the context of homotopy theory as well, but somehow saying principal fiber bundle helps me to understand what's going on. And again, we have this idea that the Tanakian viewpoint towards these torsors or to these principal fiber bundles, it's all in terms of thinking of this associated vector bundle functor, that is the Tanakian manifestation of a torsor or of a principal fiber bundle. So I think I'm totally running out of things to say. Anything you want to say before we quit?
Nope.
Okay. I'm hoping that being calmer this time actually did help the thing make more sense.
Yeah, it was definitely better. I mean, I think everything is always better in time.
Okay.
Yeah. Just because it's the second time, it's automatically.
Sure. First time, kind of, that's the word I'm looking for.
Yeah, I joke about how it's weird how it's always the second book I read on a subject is always better than the first one. So sort of like that.
Okay. So thanks a lot. I'll see you hopefully next week.
Yep.
Okay.
No.
Okay.
That was fun.
Okay. Bye.